Hello there. Today we are going to talk about symmetric polynomial. First of all, what means polynomial is symmetric? Means that if we change variables, making like permutation of them, like shown in this example, but for every permutation, you'll get the same value. Every permutation, every. It means this is symmetric. Let's take a look at a few examples. Obviously, if we swap x and y, x and z, y and z, you'll get the same value as it is, obviously. The same thing works there. This fact we don't need to prove because it's obviously, but maybe we can work with these polynomials. Let's try to define their base, like like vector space. Look at this thing is a vector space and make its base for three-dimensional space. I know it sounds strange, but it is really interesting idea. We'll take a look at the base polynomis, which are sum of the first powers, sum of all the permutation of the first powers, which is like this, sum of all the permutation of the second power, where variables are different, same thing for 3, and so on and so far for many dimensional space. I'm going to under the one dimension to just show how does it work. It works like this. Oh wait, we have the another base element because now dimension is one higher. Well, let's take a look at a few properties, theorems, and so on. So the first fact we're going to try to check is that we can decompose every symmetric polynom by using sum and product operators and the base polynomials. For example, our dimension is 3 variables, and our base is this. We are given some polynom and we are going to decompose it. So firstly, let's know that we take a look only one term. Now it is not just one of terms. This term which has been sorted firstly by x power, highest x power, secondary by highest y power, and then the highest z power. And before this all, its term power, sum of powers, is the highest. Between them all, it is sorted by x, y, and then z. Like this one. So let's decompose it with our 3 power, 2 power, and 1 power, one of terms. Like shown there, we have no second power, set, but we have third power and first power there. We can decompose it, it is obviously, and one interesting thing, we are going to cancel not this one, we are going to cancel p3 at third power times p1. And what shall we get? By cancelling this thing, we will get rid of this term. But it is symmetric, it means ahead for every permutation, it means we can swap it with y and with z, and all the terms are hidden there somewhere. And if we cancel this thing, we will get rid of this term and its reflections, how do you call them? Its permutations. We will get rid of them, and what will we get? We will get that there are no more such combinations, like 4, 3, and 3. If something another appears there, we will do the same thing, we will cancel, 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 and then power will be decreased. Power will decrease, it will become less, and we will do the same thing for the less power, and the same thing for the less power, and then we will go to the first power, which is p1, and cancel it, and get 0. For example, after cancellation, we will get the same power, but another combination. We'll cancel this thing out, this thing out. This is how we got it. We'll cancel this thing, and we will get rid of all this those terms and their permutations, reflections, call them whatever you want, and you'll do that for every terms with this those power. But there's one distinct thing: they're countable. It is choice 3 of n. No, it's choice 2 of n because we chose 2 points to separate variables. We choose them, we do whatever we want, and we get all the combinations. And it is finite number. This finite number means after making at least those times, we will get rid of every terms with those power, and we will get to the less power. But we will do it again, again, before we get uh, 0 power, and we'll be done. We'll be done only if f from 0 is 0. It means we have no constant out of polynomials. If all the variables are 0, we'll get 0. Else we have to add that to our base a constant. Then we will do it with every polynomial because we will left after all the operations will be left with a constant, which will cancel and have fun. Almost forgot. If you see another constant between the term, just multiply it by the cancellative part and you'll get no troubles. It works for every number of variables. You can check it yourself because this obviously means we can work with many dimensional space of variables, and this is obviously. So let's take a look at the thing as P. P is a sum of powers of variables, and B is our base polynomials. And let's take a look at a few equations. First is obvious, second is some difficult but still obvious, third is not obvious but you can check it and get the same result, but can we generalize it for any power? Yes, we can. First of all, let's move everything on the one side of the equation and set it equals 0. Let's rewrite this exactly term, for example, or another term which is between the first and the last because they are different, but middle terms are very close to each other, very similar. Let's check it. You can expand it like all the polynomials with one variable power of I plus 1 plus all permutation hidden there, and usually that's plus with I power, the same thing with permutations, and with everything. We have nothing another, just all the permutations. That's why we can cancel it. Yes. So let's call them like I plus 1 and I, and we'll be left with this. Also, it works where I plus j is a fixed value, because else we need to write this first variable and the second is their sum. If you don't want to use it because their sum is always the same in the one equation, it means power of these polynomials will be always the same. R3 is always R3 whatever you take it. So let's rewrite these two terms right there by using this formula and add this one and cancel this one, and those R2 will cancel. Or we will do better, we'll cancel this one and add this one, because you know R3 is +3. Do you want to know how? Because R3 is where all the terms goes with power 3. In each term, we can make in each term one variable with value with power 3. And power of our polynom is 3. It means we have no other variables. It is P3. R3 equals to P3. That's why we'll just add a date and this whole thing will cancel except R1. We'll talk about it later. So let's take a look how have we got this R1. This R1 is P1 times P2, for example, in this case. Means x plus y plus z time x, y, z plus so on so far, because we wouldn't like to check the R2 where x goes with the second power, because it cancels, as you have shown. We will check out and watch only first power. But you can see that after permutation, it will be the same. I mean, yxz, zyx means there will be 3 terms like this, because permutations, seriously. A permutation changing this variable permutation z, I mean x, y, and z, and then we can find something. This thing is not the maximum power. It is always less than 3, because it's 2. It will be less. And if it is less, then we can always make terms where we haven't met x there. That's why it is 3xyz plus powers of x, y, and z bigger than 1. Means this is our R1. Let's do it. Also, note that the 3 number, how did it appear? It appears there because of the powers, because sum of I and j is 3. And because you have got 3 variables, because we have I plus j always equals to 3. Check it out. 2 plus 1, 1 plus 2, and so on. We can make it on power 5, power 6, and we will get the same result there. If their sum is the same as 3, we'll have there always 2, 1, 3, 5, 1, 6, million, 1, million, 1. But there everything cancels, it means it's 0, just like we have shown. So what about where, for example, where variables are more than power at suburbs, but where power is much more than the number of variables? For example, there we'll have only 2 variables, x and y. Will it work, or it will not? Of course it will, because there we can say it's f of x, y, z is 0 for all x, y, and z values, but it means that f from x, y, and 0 is 0. But you can write it as symmetric polynom from x and y, because you can swap them and you will get the same result there. It works for every variable. You can cancel one variable everywhere. You can cancel few variables. You can get rid of so much variables as you only want, even being left with 0 equals 0. F from 0 as vector equals 0 as number. You can do it, but no reason, but you can do it. How can we work with this in the real life? If we need to calculate p of the high degree, we calculate by using the main base symmetric polynomials p1. Then by using p1 as we have calculated yet, we can get p2. Then we can get, by using them both, p3, and so on. You know, like in dynamic programming, means it is very useful fact. It's useful theorem. But there is an alternative way to prove it. You know that B looks like main polynomials where you open the polynomials in the form like this. You'll get base polynomials of A, B, and C with powers of x. It means we can use it, right? Firstly, let's use it for three variables x, y, z, but you can expand it if you wanted to subverse. It looks like this, but you know, when q equals x, q equals z, q equals y, we sum them all, we will get the same thing very easily. Very easily, if we sum them, we will get those p3, p2, p1, and yes, 0. But know that if we set the x, it will be 0. Means all of them are equal to 0. We'll sum them and get this thing. Yes, it is. It is the alternative proof, because you have to, firstly you have to know that they're the same polynomials, base polynomials, from opening polynomials. This is first power terms multiplication. Then you have to understand how to do this. It is easily when you know how to do this, but it is rather difficult when you don't know the trick, and because it is not obvious when you don't know it. But now you know. Don't forget to hit like, subscribe to my channel, type a commentary, and on this note, goodbye.